Thanks, Module. I also we should thank Scott Kenny, who was the person in the math department who really was involved with helping us set this up and really made it relatively painless to organize everything. So, and he's the one outside making sure it goes relatively smoothly. So anyway, it's as Module said, the atlas was a huge achievement and has had a huge impact on computational group theory and group theory in general and applications to other things. And so it's great to celebrate 30 years of that. So, and speaking of finite simple groups in particular, our first speaker had a little bit to do with that. I don't think I need to really say too much about him, but so our first speaker is John Thompson from Cambridge, who's going to talk about, his title is Reminiscences.
Oops, it's a bad start. You know how to fasten this thing on? I seem to jiggle it or something. Oh, I got it. That's it. Okay, thank you. Thanks, Bob. Well, if I had taken on board more carefully the title of this conference, I think I would have given my lecture title as 30 Years of the Atlas and Before. Because there was a time, not so many decades ago, when nobody knew about the Leech lattice, nobody knew about the Atlas, and nobody knew about the role of moonshine in theory of modular functions. Now we know many things. Those of us who looked at this material that has emerged very largely as a result of Conway's work. We can say, in a certain sense, well, in a definite sense, we definitely know much more than we knew 30, 40 years ago. At the same time, however, this is a phenomenon which I think is very common in mathematics and also in physics, that as you learn more, one of the things you learn is how little you know. That is to say, this material that we're going to be discussing it generates a lot of excitement, but it gives us an awareness of the many other questions which we still cannot answer. So I want to go back a little bit, maybe 50 years or so, and say a little bit about some of the background work that has led in a very direct way to the sporadic simple groups and to various questions about algebraic systems some of these questions have been answered now, but many other things are still unknown. Now, there was a term that was floating around in the Pentagon a number of years ago, where they used the term unknown unknowns and known unknowns and known knowns. So, well, I think to some extent, we're in mathematics, we're in that situation too. We have things, we have plenty, thankfully, we have plenty of known knowns. And the number of known unknowns is certainly increasing. And we can say nothing about the unknown unknowns, almost from the definition of what the terms mean, if they mean anything. So I'm quite aware of the existence in current mathematical research of plenty of known unknowns. And these attract us, attract some of us anyway, and one of the ways to defend yourself against being overwhelmed with the proclivity and the massive number of known unknowns is simply to say, yes, I know these things are unknown, but I don't give a damn. You don't need to be interested in everything, really. If you are interested quite literally in everything, then you're probably on the road to insanity. So one makes choices about what psychic and intellectual efforts we as individuals will bring to bear on those known unknowns that assail us. Now, when I mentioned going back before, I want to go back to what I think of as one of the influential things for a while in finite group theory, which really didn't occupy that many people, really. But we go back to the Mathieu groups. These 5 groups sat there by themselves in some sort of isolation for almost a century. I mean, I'm not quite sure of the chronology. But I was struck by a remark that Garrett Berkhoff made, which not in my presence, it was something I read, if my memory is correct. When he was beginning mathematics, he eventually did quite wonderful things, really. But he was advised by a man whom I may be giving a disservice, I'm not sure, but I think the man's name was Manning, that the main, or one of the main areas of research in finite group theory would be to bound the degree of transitivity of a finite group. Well, Berkhoff went off to think about Poincare and other things, but so I don't think he spent too much energy worrying about multiply transitive groups. But surely it was the existence of M12 and M24 in particular that suggested to Manning, if that was, or to others at the time, that multiply transitive groups were exceedingly interesting objects. Now, I certainly wouldn't gainsay that, but what we now know is that the M12 and M24 are the only 5-fold transitive finite groups at all. So that, well, that's right. Other than the symmetric and alternating groups. So among the sporadic simple groups, that's very easy to check. Only those 2 are 5-fold transitive, but there are no others at all now. So you might say that Manning was emphasizing the wrong sort of thing. But it's easy to say that after the fact. I don't know what sort of research was done into multiply transitive groups. I mean, we have on the record those 2 Mathieu groups. Whether other people were involved with this, probably, if they were, nothing came of it. Because while the empty set is interesting in some ways, it's not going to really be that exciting. So there are no more of these multiply transitive groups. So, well, what do you do if you decide not to pursue that line? Two of the sporadic groups that were discovered were by the Hall-Yanko group and the Higman-Sims group were discovered. Well, I'm not sure how they were discovered, but they have the property. Each one of them is a permutation group on 100 letters, and they're so-called rank 3 groups. That is, they're not doubly transitive, but the stabilizer of a point has 2 orbits other than the trivial orbit. Now, as it happens, those 2 sporadic groups were discovered pretty much, I think, within 1 year of each other, which is was a shocking thing to me, really. I mean, a coincidence, really, that these 4 people working on these rank 3 groups, I don't think they were conferring with each other, and nobody put a bee in their bonnet that 100 was a good number to look at, really. Anyway, that you could say, in a certain sense, I mean, this might be a stretching thing, but in a certain sense, rank 3 permutation groups are something you might turn to if you've given up on doubly transitive groups, which you can call a doubly transitive group a rank 2 group, really. So, okay, well, that's one way of sending out some trial runs into a different direction. Now, as it happens, I'm not really sure what sort of work went on with Higman. I know Higman, I have a lot of respect for Don Higman and for many other people, actually, of course. But Higman had done things that led him to some insights about rank 3 groups. And I suppose now we could, it may be, I'm not even sure of this, that we can classify all rank 3 groups. I think among the classical simple groups there would be a number. Okay, so that would be a step beyond, chronologically beyond Manning's approach, really. And then from the next step, and I'm sort of thinking of this reminiscences, would be the symmetric groups. Well, symmetric groups, which are these uniform things that occur all over finite group theory, of course. You can embed every finite group in a symmetric group. And they, of course, are often given, can be defined by generators and relations. You have a collection of involutions, and any pair of them, any 2 of them either commute or have a product whose cube is the identity. And you can, so that's a collection of groups, really. You define with finite groups with this condition. You call those 3 transposition groups. And it was Fisher who I think when he started this work, he was hoping that I don't know what he was hoping, really, but he thought, and maybe Reinhold Baer gave him this problem, I think that's possible, that he would end up mischaracterizing the symmetric groups. So, but you look at it very hard, and you first of all realize, and I think maybe it was Steinberg who put Fisher onto this, I'm not sure of this either. I'm not trying to be historically accurate. I'm not trying to be inaccurate, but accuracy is not too high in my agenda, really. So anyway, Steinberg was aware that the unitary groups finite unitary groups and characteristic over the field of 2 elements have such a set of elements. So there are 2, 3 transposition groups. So you have now the symmetric groups to contend with the unitary groups. And then Fisher, who studied this problem systematically, really, eventually came up with some new simple groups. These were also some of the sporadic simple groups by being led there initially by this classical thing for characterizing for defining the symmetric groups, really. So these two things, the rank 3 and then the 3 transposition groups, and Fisher went on to, and Timmisfeld and others, to study 3-4, what they call 3-4 plus transposition groups, which is also a topic of some interest, and sweeps out a number more simple groups, and represented a lot of research over a period of time. So those two approaches, the generalization of multiply transitive groups to rank 3 groups, and the generalization of the symmetric groups to the 2-3 transposition groups, definitely led to some new simple groups. Now the other two things that I want to mention in this regard, and the last one is the one where John made such a wonderful contribution. So there are two further things I want to say about this way of trying to grapple with finite groups. And so the third way, as I think of it, I attribute to Bauer, pretty much to Bauer, and it's the way of trying to characterize groups via centralizers of involutions. Now, Bauer made one of the lectures. He gave one of the lectures in the Amsterdam math conference in 1958. I think it was 58. So this was just not all that long after the war. And Bauer mentioned this theorem, which I've always liked, really, and it seemed to lead to many things. He considered groups such that the centralizer of involution is the same as the centralizer of an involution in PSL 3Q, or for some some odd prime power. And he announced in the Amsterdam conference that you have a simple group with an involution that has the centralizer is the same as it is in PSL 3Q, then it is PSL 3Q, except in one case, really, where Q is 3, and M11 has this property as well. So there is a real, in 1958, there's a real bump as it happened. So, well, I think at that time, 1958, the term sporadic simple group had not been invented, really. But anyway, the 5 Matthew groups were known, and M11, in a way, you could say M11, it's the baby Matthew group. It's the one of the smallest order, and so now it is now and forevermore intimately linked with PSL 3Q. And that's something the human race knows now. It did not know before. Anyway, to me, that was sort of the beginning of the centralizer of involution game. And it was used very effectively, of course, by Janko. I think you could say maybe in all 4 cases of Janko's group, he was examining extremely closely centralizers of involutions. Good. So there's that. So that's the third method of trying to get a grasp on finite groups, or in this case, the third case, especially finite simple groups. Now the fourth thing that I was thinking about, which is, I left something out. I should have. I mean, I'm embarrassed really. I'm leaving out a lot of things here, but on the question of gender, at some place in this game, you have to mention, you should, it's appropriate and mathematically sensible to mention Coxeter's work. The Coxeter groups are quite wonderful things. They have geometric things associated to them. Coxeter he was a diverse fellow, and so the Weil groups of the simple algebras fit into the framework of Coxeter groups, and so that would be in the same arena where I was talking about Fisher's groups. But in this fourth case, in a way, it's the biggest one of all, and I want to dwell on that a little bit. The most natural way, the thing that just gets you right where you're living, is to define a group, is to have some sort of object, a geometric object or anything that you've cooked up really, which has some sort of structure and a notion of isomorphism, so that the group of isomorphisms or automorphisms or homeomorphisms or whatever of this system is an underlying thing for the group that you're studying, or if, as it happened historically, these objects swam into human consciousness, then which a priori don't have anything to do with even the notion of a group, really, but they have something that we call symmetry. The notion of symmetry is just so fundamental to rational thought that you can't, you just hesitate to quantify it, really. And of course, the classical example of these things are, of course, the 5 Platonic solids. And the symmetry groups of the 5 Platonic solids live on, and even into the 19th century, where this remarkable book of Felix Klein, the icosahedron, came about, and lo and behold, you find modular functions discussed and elliptic functions, of course, in Klein's book. But the title of the book is the icosahedron, which he was certainly aware goes way back to pre-Christian times. Tietz made a massive effort, with my limited understanding of these things. He introduced the notion of a building. It has apartments and panels, and there are experts in the audience, the theory. But so a building is a thing which has attached to it a group in a way that Tietz developed very well. It's a really basic thing, and Tietz very over a period of years, he and his students developed this theory extensively. And another person who, to my way of thinking, made a central contribution is to build something underneath. You might think of it as being underneath anyway, something associated to a group which has some structure, and then the group acts as automorphism of that structure. And that, of course, is Chevalet's work on getting a basis for simple complex Lie algebras, whose multiplication table consists of integer combination. So you get a multiplication table basis for a Lie algebra, such as the product, Lie product, expressed in terms of the base element as a linear combination with integer coefficients of these basis elements, and then you can tensor over any field of your choice, really. And in particular, you get all the classical finite groups in that fashion, really. And now you toss in twisting with these Lie algebras. Some of them have a finite symmetry group, and you get the twisted groups as well. So, and Chevrolet, I don't know what the relationship, I never, it's not the sort of thing I probed about, but I never explored what the relationship between Chevrolet and Tietz was, really. I mean, they were both in, they were certainly aware of each other. The underlying thrust, is the way I think of it, is the same, really. Although the working out of it is remarkably different, really. And then we come to this Leech lattice now, or you could say initially, you might say more generally, you might talk about, or I would think of, been led to this, to think about unimodular even lattices and their isometry groups. And I think the first one you would run across would be the E8 lattice, whose automorphism group is the Weil group of E8, which is associated with the Lie algebra E8, and which is sort of you might call it a sporadic Lie algebra. I don't think people say that, but I mean, it's one of the Lie algebras, E8. And then you can glue things together and take direct sums and things. But then what Conway did in a superb thing, which linked up with the 19th century in a great way, and exploded with the great success in the 20th century, is the Golay code. The Golay code, which goes back to Steiner, I think, in the 19th century, and Leach must have used that to build his lattice, although maybe his motivation was sphere packing or something. I leave that to historians, really. But anyway, John took that thing apart, really. And at some point, maybe not when he first got it, you can correct me, Conway, if at some point there was a development of a thing which they called, I don't know who did it, whether it was John or Simon or someone else, the octad generator. Where here's a great thing. You give a 5-element subset of the integers from 1 to 24, and there's a unique 8-element set, the associated octad associated to that 5 set, really. Now, that was something that comes from Steiner, really, that every 5 sets containing a unique one of these things, which is called an octad. And if you need to study these things in great detail, it'd be nice to have an algorithm or some trick to go from a 5 set to an 8 set. Well, there is such a thing, or at least, and at some point in this work on the Leech lattice, this octad generator came into being, really. This is something the human race now has forever. So, and that's one of the grand, I think, working things on the sort of the underpinning, and well, anyway, however it worked, out of this came the group of symmetries of the Leech lattice, which has many characterizations now, anyway. But the but the group is now called Conway 0, or was that a Conway dot? Or anyway, it's the non-simple one. It has a central element of order 2, because every one of these even unimodular lattices has a central involution, namely just minus the identity matrix. So you factor away that central thing, you've got the Conway 1, and that's a new simple group, and it has some other simple groups inside. So this was a way that you found the underlying object whose symmetry group is the group you want, but you need to understand what this underlying object is really, and so this is how Conway, I think, got into the game of not only keeping track of the sporadic groups, in particular their character tables and their maximal subgroups, but he found some new groups himself, really, and maybe I don't know when or if it's. See, why does this process stop? I don't think we really know why it has stopped. Whether there are these 26 spread. I mean, maybe there's nothing to explain really. It did stop. It's like other sporadic things, other anomalous features of the universe stop really. But surely, if you found more than one finite simple sporadic group and know the rudiments of representation theory, then it certainly makes sense to gather together the information which is building. For example, with Yanko's group, Yanko sent me a letter once when he said, I'm the world's best expert on multiplying 7x7 matrices over the field of 11 elements. I mean, he had to look at quite a few, really. And also, Yanko's thing, what he did, it was a pretty thing, really. He found all the Bauer trees associated for all the primes, for all the odd primes, and it was in that way that he found the 7-dimensional representation of the Yanko group over the field of 11 elements. So, and when Steinberg heard of this, by the way, the order of Yanko's group is 55 times 56 times 57. It should be a triply transitive group. It isn't. But and Steinberg's view was this is a severely twisted G2, really. so you get into this game, and so material begins to build things that are precious to us. I mean, we should be proud that these things have been found, really, and it's just a wonderful thing that so many properties and features of the sporadic simple groups have been incorporated into the atlas. Now, there's a remark that I noticed some time ago in the atlas that I think was a very astute remark. There are many, but this is one I found quite good, really. Say, well, this is this thing with the printout of the character tables and comments and things, some diagrams. Say, well, what about the question of errors? See, it's a pretty elaborate thing, and I think it was in talking about the character table of the monster that they mentioned that if we assume that there's a printer's error once in every 1,000 items that are typed into producing this character table, then and it's very, so that's one in 1,000 is pretty good. One error rate. They said, well, then we have 300 errors. So they owned up right away, say, look, be reasonable. I mean, we were doing the best we can, and you put out this thing, this atlas, to the mathematical community, and it's partly our responsibility, as well as the ones that write the book. Well, you want to check out the thing, and if you find some slips, okay, well, you notify them. And I don't know whether there have been notifications or not. Somebody mentioned, probably you wrote it, John, that they did find some mistakes in one of the held simple group or something. Actually, the character table did have side step, because you work on these character tables, and it's a lot of fun to look at the orthogonality relations and squeeze them for what you can. But of course, errors can slip in, or even conceptual errors. And anyway, people in this audience, you don't need me to tell you that it's a wonderful extended piece of work which treats all 26 of the sporadic simple groups and a number of other of the simple groups, in particular some of the PSL2s, which were first came to the awareness of humanity in the works of Galois, really. The PSL2P and PSL2Q, they come into many cases. And so a number of character tables of these groups, which you can find elsewhere as well, are incorporated into the atlas for very good reasons, it seems to me. So we have that. Okay, well, these are things which are these are part of the known knowns, and these are the known knowns that we have. But I would also say about the atlas that there's some known unknowns that come upon it. And these surely will exert interest to some people in any case, maybe not a great swath of the mathematical community, but I would anticipate, because the title of this conference, for example, is 30 years of the Atlas and Beyond. Well, I'm assuming the Beyond is a region of activity, not indolence. And so there will be things that come into the play there, and and a number of these things, I think, could very well be traced back to suggestive things that were in the atlas. And finally, of course, I want to reminisce a bit about the monster. I'm not sure what the chronology is, but there was at one point where several of us, I think it was at, maybe Fisher encouraged this, or Conway was especially interested in it, where we, my memory tells me, I'm not sure I believe it, but my memory tells me that we hired some sort of van to take half a dozen of us, and we tooled off to Bielefeld. Do you remember anything going to Bielefeld ever?
I remember the van. I remember going to Bielefeld, yeah.
You don't remember getting the van? Okay, well, anyway, there were several of us ended up going from Cambridge to Bielefeld, and Fisher and his circle were there, and it was just, I think this is just when the monster was being born, I don't think I remember much of anything except the van, really. So I'm not sure that should be believed. But I mean, of course, Fisher, I've known Fisher since he was a graduate student. And he's a serious fellow. And he was getting on to something which I think was beginning to look like something connected with the monster, which turned out to be the monster. And anyway, we did get to Bielefeld and listen to some lectures, and maybe some were given as well. And eventually, this group came into being, and its character table was constructed by Livingston, I think, with the computer. Did he do it himself, or?
Well, Fisher was involved.
Was he involved in that too? Yeah.
And then there was also a student of Livingston's called Thorne.
Yeah, right. So that's it. And this led to that remark, a pregnant remark that John Mackay had about the 196883 and the 196884. The first number being the degree of an irreducible character of the monster, and the second one being the coefficient of Q in the Q expansion of the elliptic modular function, really. And John and Simon took that, and they ran for the goalposts, and I think they used some stuff from maybe Atkin got in there, and Fricka. Anyway, the upshot is that to each conjugacy class of the monster, you associate a modular function, which is a generator for the function field of a genus 0 subgroup of the modular group of PSL2. And so this is a thing which Grice took and constructed a representation, infinite representation of the monster, which explains these things. And Atkin, I think, was involved somehow in that too. Atkin I just learned, I hadn't paid too much attention, I just learned that Atkin died not so long ago, really. But he certainly, you see, you can, if you have a class function in a group, then the Bauers characterization of characters gives you, in principle, gives you a way to check whether that class function is the trace function of a representation. You have to check on the so-called elementary subgroups. So anyway, a tremendous amount of work was done there. And it seems to me that we're in some sort of limbo still in this area. And so it's way beyond me. The study of vertex algebras and whatever. But it seems to me maybe it would be nice, and Conway has said this himself, really, it would be nice if there were some object, some presumably topological object that has some sort of group of homeomorphisms which could single out the monster, really. Well, if there is some sort of topological thing like that, it hasn't been found yet, as far as I know, really. And there is certainly a huge interest, not in this group, I don't suppose, too much, but in some other parts of the math world, in vertex algebra operators and things that Bob Grice has been working on, and others, and Frankel, and a number of other people, really. But certainly at the beginning of this saga, however it ends, with the monster. The beginning of it was influenced in a very major and beautiful way with the work of Conway. And I realize this is really a rather disorganized lecture, but what should I say? I mean, it's disorganized, but it has the great merit that it's heartfelt. I don't know whether that excuses shortcomings or not, but anyway, that's where I stand. Thanks a lot. I'll stop.
Any questions or comments? When you were explaining how people found some of the spread groups, or how did you find the Thompson group? What was your motivation for looking at it?
Well, it was just it's a subcase. I mean, just from the centralizer of an element of order 3 in the monster. Yeah, I mean, and the only reason that it was a cornucopia. So looking at the monster and its subgroups, really, there was room enough for everybody.